Thank you very much. Thank you for the introduction. My name is Kento Sato, and I'm a team leader of high-performance big data research team at RIKEN R-CCS. And to outline this feasibility study, the RIKEN system research team has three groups. That is architecture research group, and system software and library research group, and the application research group. And then I am a group leader of the second one, the system software and library research group. And today I will briefly introduce the research plan and the schedule in the system software and library research group for this feasibility study. So the goal of this group is to identify which system software should be developed in domestic or developed through international collaboration based on development cost and current software usage status in Fugaku and other major supercomputing center in Japan and in the world, while considering existing system ecosystem surrounding candidate architectures. And then we would like to define system software development roadmap for the next generation system. So we cover a wide range of system software area. Our group covers following system software fields: scheduler and runtime, I/O storage and file system, operating system and virtualization, communication library, compiler programming model, and numerical library, and AI frameworks. So as shown in this organization structures, each this subgroup is led by expert in the system, so each system software field, and the collaboration among RIKEN and other national labs and university, as shown in this figure, like Nagoya University, Tohoku University, University of Tsukuba, NII, and Osaka University, and Kyushu University. So under this feasibility study, we mainly conduct three research items. The first one is investigation of system software trend. So in this item, we investigate existing and future system software trend in terms of portability, productivity, and performance. And also, at the same time, we investigate current system software usage status of system software in the Japanese HPCI systems and other major supercomputing center in the world. And also, we collect necessary information to decide software development strategy. So, I mean, even if we design and develop a state-of-the-art like system software architecture and processor, they might be useless if there's no system software making use of this architecture and hardware and CPU and GPU. So one thing we have to do is to define development strategy for given candidate architecture for the next generation supercomputers. So I mean to decide which system software to be developed in Japan or developed through international collaboration. And if we decide whether we develop in Japan or international collaboration, we also define strategy such as which this software should be developed under proprietary by vendors, or we are allowed to use existing software ecosystems such as open source software as it is, or we also need to investigate. We have to port or tune for specific architecture to deploy the system software, or if need totally new software, we have to develop that software. So we have to, which software has to newly develop it from scratch. So that information is very important to estimate the software development cost, because software development costs a significant amount of money. And then last one is investigation or difference of similar software. So if APIs of system software are standardized, standardized, we can provide the almost same similar development environment regardless of choice of its implementation, like in MPI. So MPI are, as you know, standardized by the MPI forum. So we can provide almost same user experience, whatever MPI implementation we adopt for the next generation supercomputers. Well, whereas if APIs are not standardized, we need to investigate the difference across different implementations. For example, there are many numerical libraries. So let's say we have one MKL by Intel and SSL2 by Fujitsu. So Intel x86 CPU and Fujitsu ARM will come with numerical library to make use of their CPUs and architectures, but they are not standardized among them. So we need to investigate whether one MKL and also Fujitsu's SL2 can provide the same development environment. And if not, we need to figure out what implementation lacks to the other implementation, so that we can know the impact to user. Most of the Fugaku user use SSL2, which is tuned for the Fugaku CPUs. But if we transition from ARM CPU to, it's just for example, x86, that will impact to user development. So we have to how impact will incur to application developer by identifying how difference happens between these two similar numerical libraries. And numerical library is just example. We should have many system software that are similar but slightly different that we need to identify. And for the investigation of the existing software and future trend, each subgroup investigated them. So let me introduce each of them. The scheduler and runtime subgroup consider diversity in HPC application and their job execution method. Also, they study the trend in job scheduling technology as well as new requirement from new application domains such as complicated workflow, combining scientific simulation and also AI training and inference. And I/O storage and file system subgroup study storage access pattern, I/O pattern in wide range of applications, including traditional HPC application, as well as big data and AI application. And so because system software running on storage architecture is tightly coupled with underlying storage architecture, so in this group, they also design a storage system from software to architecture, considering I/O performance, power consumption, and development cost under collaboration with storage and device vendors. And operating system and virtualization and cloud subgroup consider the state-of-the-art virtualization technologies such as containers deployed on top of accelerators and many core architectures. And they investigate operating system and virtualization techniques for the next generation supercomputer in terms of performance and power saving and usability and security. And HPC environment investigation subgroup investigate the current status of system software environment deployed in Japanese HPCI centers, including Fugaku, and also a major supercomputing center in the world. Then we clarify what system software are required in future, considering requirement from a wide range of application domains, including data-driven scientific application, real-time processing, application combining AI and simulations. And communication library subgroup consider network technologies expected to be adopted in the next generation systems, and they investigate interfaces and implementation technologies in emerging communication libraries. And compiler program model subgroup That group investigate following items with tight collaboration with the architecture groups. We investigate needs and trends of application development in terms of programming language. And also we study existing code generation techniques, including open source compiler and also task-based programming model. And also we investigated programming frameworks enabling high portability, including performance portability across various candidate architectures. And also we looking at other programming tools such as tracers, debugging tool, and profilers. And then we finally clarify programming environment for the next generation systems. A numerical library group literally investigate a numerical library required to develop applications, working with application group. And lastly, AI and framework subgroup investigate AI frameworks and tools and numerical libraries to efficiently run AI workloads. And on the next runs on next generation supercomputers. And so we recognize tight collaborations are important to co-design the architecture and the system software for the next generation supercomputers. So working with architecture research group and also participating vendor, we share some information with architecture group with candidate architecture, and also low-level system software that each vendor is plan to develop for their architecture. And also our team will give feedback upon our investigation to the architecture group. And also understanding requirements and needs from application developer and its user is important. So we also currently doing requirement survey to the application group. And this is the overview of the final report out of this feasibility study. So, addition to the report describing detailed explanation about each system software and libraries, we also make a table to clarify which system software and library are provided and given candidate system architecture. So first we determine what system software should be supported based on our investigation result. And then we list all the necessary system software that we need to support in the next generation system. And then receiving some candidate architecture from the other architecture research group. Like this is just example, so they are not necessarily correct. But let's say we may have x86 architecture, system architecture, or ARM-based system architecture, or we may have ARM plus some accelerator with chiplet technologies, and also many other like x86 or ham plus GPU. And by filling out, we fill out this form how we develop and provide this system software. For example, like GCC, if we employ this architecture, the GCC is used as open source as it is, so we don't have any software development cost. Whereas if we newly need to adapt some GCC to like new ARM9 instruction set, we need to port the existing compiler to new architecture. So we need pay some cost for software development. Likewise, some system software may be developed under proprietary by vendors, so we may not need to pay a cost out of Japanese budget, because vendor invest for that software. So, and also, as I said, we also have to investigate differences among non-standardized but similar software, because even if we provide a numerical library, performance and usability may differ. So we also have used that information as trade-off analysis when we finally select architecture, considering software ecosystem and the usability of the system. And also, some software are tuned for one architecture, but not for other architectures. So, for example, this is just example. It may not be true. So, for example, NumPy, thanks to the software ecosystem and open source community, NumPy is well tuned for x86 CPU. But it's not necessarily it's well tuned for ARM CPU. So even if we employ the same system software like programming framework, we may not need to tune any single architecture, but we may need to spend a significant amount of money and time for porting and tuning this framework. So we have to identify which software has to be put considerable time and money for development, tuning, porting beforehand we start the development. So with this table, we believe we can clarify what system software and library are provided given a candidate system architecture with some idea of their software development cost. So this is the last slide. This is 1 year and a half project with potential 1 year extension. So towards the interim report, we are finishing completing survey of system software and technology trends, as well as system software usage survey across different Japanese HPCI supercomputing center. And after we pass the evaluation committee, we also transition to define system software development study and also investigate difference between non-standardized similar software, and also consider to prioritize which system software to be supported in future system. Then we put them together in the final report with some collaboration from with architecture research group and application research group. And with that, I will conclude this talk. Thank you very much.